Okay, we already looked at marine heat waves in a few podcasts, mostly from the impacts, physical aspects, predictability, and so on. And I always say, how can we take action even if there is a good prediction, let's say around a coral or a fisheries zone or a coastal ecosystem, and so on. This is a nice review, which means it's a nice long article with lots of very nice references, and as usual I'm going to reduce it to a simple summary, brief introduction, so that you can follow up if this is of interest to you and you want more details. So it's a review article from Nature Reviews Biodiversity, Marine Heat Waves as Hotspots of Climate Change and Impacts on Biodiversity and Ecosystem Services. Okay, let's read the abstract and run through a few figures, and then we'll read a little bit about future directions. Intensifying marine heat waves are pervasive and destructive. I shouldn't have broken the sentence there. Intensifying marine heat waves are pervasive and destructive manifestations of anthropogenic climate change. There we go. Over the past 2 decades, MHWs, marine heat waves, have driven biological, ecological, and socio-economic change in almost all oceans and seas. This is important because it started with one paper, I think by Nikki Gruber and gang, and then there is a bandwagon now where people are finding marine heat waves everywhere, and there are lots of papers, but not all of them necessarily focus on the impacts. And remembering that ocean has high heat capacity, slow moving, then heat waves on the land are very different than the heat waves in the oceans, and so on. Keeping all that in mind, in this review we assess the impacts of MHWs on marine organisms and the benefits they provide to people, that is ecosystem services, and they highlight knowledge gaps and consider opportunities to mitigate MHW impacts, which is critical in the end. Globally, MHWs have become increasingly intense and frequent and result in mortality and movements of species when acute temperature thresholds are exceeded. So I've gone back and reprocessed the marine heat wave. I'll be speaking and it won't be recording, so sorry about this. I'm having some technical issues, and this happens often after an update, software update. So these people are very smart, but they are not users, so they don't test everything that people go through, and we have to live with that. And it's not very easy to report back, because there is one big site where you can log in your complaint and maybe it'll get looked at. Anyway, my pet peeve about computers, Microsoft especially. So globally, MHWs have become increasingly intense and frequent and result in mortality or movement of species when acute temperature thresholds are exceeded. Vulnerability and resilience to MHWs vary among species, but these mortality events have been prominent for habitat-forming foundation species such as corals, kelp, and seagrass, causing many cascading indirect effects on ecosystem functioning and biodiversity. So corals host many species. Kelps and seagrasses are they have lots of co-benefits in terms of oxygen and organic carbon production, export, and generally hosting a multitude of species, which is why they tend to be also hotspots for diving and so on, right? Poleward species shifts produce novel and complex species interactions and altered ecosystem functions, which have considerable consequences for people and their livelihoods. Reducing greenhouse gas emissions remains essential and urgent to address impacts long-term impacts, but increases in MHW intensities and duration will be unavoidable and prominent for the foreseeable future. As such, closing the current knowledge gaps around MHWs and their impacts on biodiversity, as well as proactive management strategies, are urgently needed to mitigate further damage to the ecosystems and people and to build resilience into the future. So there are many issues here. One, just like on land, the species can move to higher latitudes, or they can also go deeper into the ocean, but there are many differences compared to land. On land, they can go poleward and up the mountains, but The pressure is increasing as you go up, but not as dramatically as it does in the ocean, because ocean waters are very heavy. So every 10 meters or so, you get another atmospheric pressure, sea level pressure addition, and then light disappears at some point, and then CO2 and oxygen have variability as well. So all these affect how species move, whether ecosystems move at all or they get fractured. On land we have mobile generalists and sedentary specialists, so ecosystems generally don't move, species move, so you create biodiversity losses in that sense. But in general, nature makes the rules and biology finds the loopholes, so new niches open up and some species will occupy that space. In the ocean it can be jellyfish, which is not very useful for human beings. So we are always worrying about how we will be ultimately affected by what we are doing to other species, right? So let's read the key points. Marine heat waves are periods of unusually warm oceans globally. MHWs are a natural phenomenon but have become stronger, longer, and more frequent since 1980 at least, driven by anthropogenic climate change. The oceans are now experiencing record high temperatures as warming and large-scale climate phenomena combine which combine to intensify and prolong MHW conditions. As warming and large-scale climate phenomena combine. Okay, not which combine. Anyway, I hope you got the point. In the physical oceanography and climate realm, we have seen how MHWs can intensify cyclones, for example, and so on. Temperature influences biological processes from cells to biomes. Species have evolved specific temperature tolerances that match their altitudinal distributions. MHWs cause acute temperature stress where species and populations with narrow distributions, limited mobility, and proximity to their warm distribution limits are most vulnerable. So it's not just warming rate, but how fast it's warming can determine which species can adjust, which will suffer greatly, and so on. Corals don't move so easily. No, they have ways of moving, but not on a rapid time scale. MHWs have direct impacts on species productivity and distribution, and indirect impacts through altered species interactions. Impacts on foundation or keystone species result in cascading. Sorry, I keep stressing the sentences wrongly. I need training, I guess. Impacts on foundation or keystone species result in cascading changes to communities, food webs, and ecosystem functioning. Impacts of MHWs are often exacerbated by co-occurring stressors. Could be a heavy rain event changing salinity, or a river runoff changing nutrient loading as well as salinity, and so on. MHWs have affected ocean ecosystem services, loss of fisheries, nutrient cycling, carbon storage, ecotourism, and cultural values have followed shifts in species abundance and distribution, decimation of seagrasses, corals, and kelps as well, and megafauna mortality. In a few cases, new opportunities have arisen, so you always have the biological loopholes or refugia happening or occurring. Reducing greenhouse gas emissions is the only long-term solution against increasingly severe MHWs. In the short term, preparation for increasing impacts of MHWs is required. How to actually respond to, let's say, MHW early warning, that has to be developed to manage these impacts. Emerging adaptation approaches include flexible fisheries management and swift conservation to protect vulnerable species. Future research should integrate effects of temperature and compounding stressors. So even though MHWs tend to stress temperature, usually that means you are changing density, often mixing stratification, so there are many cascades that become compounding stressors. Okay. MHW drivers and definitions. We have already looked at these, but let's read briefly anyways. Marine heat waves are discrete periods of unusually warm ocean temperatures driven by many atmospheric and oceanic processes, as we'll see in a figure. For example, high pressure systems can locally reduce cloud cover and wind speeds, leading to increased solar heating and suppressed evaporative cooling, etc., and wind-driven currents or boundary currents or reduced coastal upwelling, mixing of deeper, cooler waters, and so on can affect marine heat waves as well, or can be drivers. And these are local processes, of course, which are happening in global scale. Internal variabilities like El Nino Southern Oscillation and various other modes like North Atlantic Oscillation, and at a shorter time scale by Madden-Julian oscillations and so on. We'll see the scales in a minute, but weather systems or mesoscale ocean eddies that affect local heat fluxes typically operate on scales from tens to hundreds of kilometers and on time scales of days to months. You don't think of heat waves of months on land, but in the ocean this is very common because it's a slow moving high heat capacity medium water, right? So regional climate models and associated teleconnections can affect regional climate modes like Indian Ocean dipole, Atlantic Nino, and so on, can affect these local phenomena across or between ocean basins on subseasonal to decadal time scales. So El Nino has, centered in the Pacific but has global teleconnections and so on. There are also multi-decadal longer time scale background changes of PDO and North Atlantic oscillation that we mentioned, especially the Atlantic multi-decadal oscillation, which can remain in the positive phase for multiple decades, and then you superpose El Nino or global warming on top. You can have serious compounding effects. Defining MHWs, there hasn't been a unique definition, just like for heat waves on land. The most commonly used framework defines a MHW as warm water event at a location lasting 5 or more days where observed ocean temperatures exceed the 90th percentile of observations in a fixed long term, so about 30 years of climatological record for that time of the year. So seasonally dependent as well, but there is more and more demand for having maybe impact-based MHW definition, since even if there is a 90th percentile exceedance, if it doesn't do anything, do we really have to worry about it? Maybe from the climate perspective, yes, but not necessarily from biodiversity and ecological perspectives or ecosystem services like fisheries, right? So let's look at some did I cut out? Yeah, so this is just a accompanying picture of the MHW box, which continues on the next page. We'll come back. So you have anthropogenic warming that is slowly entering the ocean, not so much directly from diffusion, but regions where there are subductions and atmospheric signal gets taken into the deeper parts of the ocean. Diffusion is a very small effect in the ocean in general. Reduced cloud cover can do it, net heat flux into the ocean, weaker winds, reduced evaporative cooling, local warm advection, so Ekman transports can bring in warm water masses from other regions, reduced heat loss similar to heat flux into the ocean. High pressure can create a dome and you can start cooking. Large scale oceanic and atmospheric teleconnections such as Rossby waves of course can come in and move the thermocline up or down, or have ways in which they can generate warm temperatures, and there are ocean currents advection. Of course, suppressed mixing, reduced upwelling at the coasts, or reduced upwelling in the middle with Ekman pumping, and mixed layer depths can vary accordingly. So you look at temperatures here, you have some kind of a climatology and the mean may be shifting, and you have MHW maximum intensity happening here, and you can have categories 1 to 4 which have some definitions. So heat spike greater than 5 days here in this the orangish reddish color, climatological mean which can jump to 90th percentile threshold, so long-term mean may be lower but 90th percentile tends to be higher, and then you are exceeding those over durations of greater than or equal to 5 days for to be defined as an MHW, and you have intensity which is compared to the local climatology at that time of the year because seasonality matters and so on, and you have measured temperatures as well that are needed to define exceedances in the first place. Okay, so scales going from literally centimeters out to planetary scales in kilometers, going in time scales from a day or less to centuries, multiple decades at least, and you have local processes that affect mixed layer temperature budget, so exchange with the subsurface and with the atmosphere. Marine heat waves sit somewhere here with long-term climate change creating warmer and warmer temperatures, as we saw. Well, we haven't seen the trend map yet, but teleconnection processes and persistent features can bring larger scale spreading of the heat wave as well, as we saw here. And you have temperatures with a fixed baseline, so you have MHW here, and you have everywhere measured temperatures giving you monitoring data, and you cannot know a heat wave happen unless you have data, right? So here again, climatology and threshold, so detrended baseline here, and you have shifting baseline, so you have the mean temperatures themselves shifting. So even though if you take 30 years as a climatology, if things are rapidly warming and they are continuing to warm, then within the 30-year period, you may have a shift in the climatology itself, which you can call shifting baseline, or the 90th percentile may continue to shift even if annual means remain in the same way. Okay, so I'll skip this detail in terms of departures from normal or baseline temperatures. We already saw a bit of it, but you can see these references for those 26, 25, 37, 236. So you can imagine how many references there are. It's a gold mine of references. Okay, jumping ahead, moderate MHW areas, so moderate, strong and severe. So you can see there are spikes of strong and severe, whereas moderate ones happen almost all the time at some scale, and extreme ones tend to jump up in scale as well when they do, and especially also the strong one here. So it's moderate at some scale, and strong at some other scale, and severe or extreme at a smaller scale. So you have a center and then spreading out the scale of the heat wave. So and you have to remember the scales are different. So here, strong MHW area in kilometer square, this is for moderate, and this is for severe or extreme. And you can see, make sure that you are tracking the scales, but the idea is still the same. You cannot have a very large extreme heat event unless it's a real massive confluence of multiple factors, because ocean warms slowly and cools slowly, and to warm the surface or near surface, you will need massive amount of heat convergence or heat flux, or somehow you bring advect warm waters, or use a Rossby wave to change the mixed layer and so on. So in general, the scales of temperature anomalies tend to be small, as opposed to let's say cyclones or Madden-Julian oscillation or El Nino Southern oscillation, which tend to have thousands of kilometers in the atmosphere, but hundreds of kilometers in the ocean in general. So here, moderate, strong, severe, and extreme, and there are some hotspots for heat waves, and this is where the whole thing started with the warm blob that I think Nick Bond first started to write about, and this is the action area for the Pacific Decadal Oscillation, for El Nino, for Indian Ocean Dipole, Atlantic Nino, and so on. So these are MHWs in time and space over 1982 to 2023 with 1 year running mean. Here is the map of maximum category attained by a MHW at each location between 1st July 2023 and 30th June 2024. So remember that 2023 was a record warm year, combination of global warming, El Nino, one of the strongest El Ninos, and multiple other factors that we haven't fully understood. And the warming continued into 2024, and 2024 was supposed to be a La Nina, but didn't quite materialize, so the warming continued. So you can see the impacts of all that global warming on. So you have global warming, where we are looking at global mean temperatures, but then you have heat waves, marine heat waves at specific locations, because all global warming is local, right? So keep that in mind. So some details here in terms of exceeding acute temperature thresholds that cause rapid mortality and distribution shifts. The species that can move will move. There are many that cannot move, like corals, and they can die, right? So low performance, high performance in terms of performance breadth and thermal tolerance range. So without going into the details here, you know that species have a certain range within which they basically live happily, but they can perform at the edges, cold edge or warm edge here in terms of temperature, but there is exceedance at which the not only the performance begins to narrow, but also they have to move or face mortality. Okay, so they have an optimum temperature around which the performance window can be large, and if you keep warming the temperature, you begin to hit the edges of performance overall, and there is a minimum temperature they can tolerate and a maximum temperature they can tolerate. Okay, so this is for cold and warm events. So you have optimal window, and based on what is happening with global warming, etc., you have species which can have a wide or narrow temperature tolerance here and different ranges, which can be optimized to cool or warm environments, here as illustrated as narrow cool, narrow warm adapted species respectively. So it depends on where you live. Narrow range here, wide range species here can manage to survive or move in this window quite comfortably as warming happen, or MHWs happen. Cold adapted ones live here, warm adapted ones live here. So you know that there are species like bluefin tuna which may live here, yellowfin tuna may live here, corals may live here but not here, and so on and so forth. Okay, so what are recorded? These are many case studies that have described rapid mortality events in dark red and shifting distributions in light red during or shortly after marine heat waves. So these include you have foundational and abundant perennial sessile species such as coral, kelp, seagrass, and reforming bivalves, rapid loss of ecosystem functions, etc. So here you have movements, lots of fish, and you can see the indicators and mortality events. So benthic invertebrates, mobile invertebrates like crabs and those, coral reefs, seagrass meadows, fishes, soft corals, marine forests, and zooplankton. Okay, you have soft tree-like corals as well as hard corals which form reefs, and both are very important for recycling nutrients and creating rich habitats. They are like the rainforest of the oceans, right? So let's leave it there. And here is a range of position and vulnerability to MHWs. We are looking at species thermal range, so cold range and warm range, and effect size, so log response ratio. And you can see there is something called allometric scaling. I don't know if I want to go into that. Warm species have certain life cycles, maturity, lifespan. Cold species are different, and there are reasons: density, metabolic rates, etc., density of the medium, where you can have large appendages to float around. If it's warm water, you will sink unless you have appendages to float, if that's the way you survive, right? So range, position, and vulnerability to MHWs. Previous meta-analysis here has shown that species-specific impacts from marine heat waves are often negative, so negative log response ratio near the species warm range in the red icons here, and positive near its cold range, so blue icons. These effects vary between taxonomic groups, so mean effect size per taxa group shown with standard errors. So these error bars are shown here, standard deviations or some form of error bar, and In some cases, positive impacts on taxa have been observed near their warm edge. So again, red icons. So again, we are looking at birds, macroalgae, plankton, corals, mammals, seagrasses, fishes, mobile invertebrates, and sessile invertebrates. So global map here showing regions with higher proportions of species at their warm range edge. So blue and low proportion, pink and high proportion. Okay. That is regions that have particularly high vulnerability to future MHWs. If you're already on the edge of survival, you have managed to move to the edge to find upper temperatures where you can still survive, and then next MHW may just push you over your limit into mortality, right? That's what vulnerability, high vulnerability means. Specifically, the proportion of species in the local species pool that were near their warm range were calculated to determine locations where MHWs might be more likely to have a strong negative effect. In other words, you know what's happening with global warming. There are projections which also come with ocean temperatures, and you are trying to estimate where we are headed. Okay, so these are the species thermal ranges, and these are the global map showing region with high proportion of species at their, these are the proportion of species at the warm edge or being highly vulnerable. Okay, so many nice details there. I'm being brief because you can go and read it. I just want to give you a brief exposure to the material, that this is phenomenal because this is considering so many previously published study, that this is based on 16,582 species globally distributed from Aquamap project, and they are gridded onto 1 degree latitude, longitude grid cells. Does this cover the number of species? Of course not. Ocean has lots of species, of course, and the studies tend to be local and often driven by commercial interests, let's say tuna or ecotourism or bivalves and crabs, etc., etc. Okay, so here, how long am I here? Maybe if I don't finish in one podcast, I might want to split it. So this is almost 25 minutes, so let's leave it here, but you get the idea that marine heat waves are basically hotspots of warming, as definition implies, but they are also generally hotspots of biodiversity impacts and impacts on ecosystem services. Ecosystem services is about us. So extracting fisheries or ecotourism, or now more and more deep sea mining and deep sea fishing, etc., which will cause other compound stressors along with marine heat waves. So we have to begin to adapt. So you have early warning time scale where maybe you can manage fisheries with those predictions on marine heat waves. You need adaptation, which means you create marine protected areas on decadal time scales, and then you have mitigation, of course, is the overall reduction in greenhouse gases, which is not going so well because 25 years of negotiations haven't really bent the curve on emissions, and ocean takes up more than 90% of the additional energy we trap because of increased greenhouse gases, and it takes up about 25% of the total carbon dioxide as well. So all these have to be kept in mind. Let's come back and wrap up the podcast in the next part. Okay.